In the previous two videos, we have mentioned and explained why the three methods work. We know that it works for square roots, but what about cube roots? Let's focus on long division. In the last video, we have explained why this method works using specific numbers. In general, let's denote the square root we want to calculate as b, and then we use a to approximate the first digit, which would then give us the remainder r, where r equals b minus 10a whole squared. Since we want the next digit to be x, that means 10a plus x whole squared would be close to b, and so we can rewrite r to be x times 20a plus x, which is why we double the quotient, write the blank, and so on. So what about the cube roots? Again, let's denote the cube root we want to calculate as b, and then we use a to approximate the first digit, which would then give us the remainder r, where r equals b minus 10a whole cubed. Since we want the next digit to be x, that means 10a plus x whole cubed would be close to b, and so we can rewrite r to be x times some mess over here, which is our new algorithm for cube roots. Let's use some concrete example, 18. Since 18 is between 2 cubed and 3 cubed, we write down 2 in the first digit. Write out the quotient cubed and subtract like you do in division. Now we need to use the algorithm we derived here. Substitute a equals 2, and we want to find out x so that this expression is just under 10,000. It seems a little bit difficult here, but here is a computational trick. Ignore the x squared term for now because it is not going to largely affect the entire product, and divide both sides by 10, and we want to find x such that 6x times 20x is just under 1000. Then simply test out values of x from a larger value until it is just under 1000, in this case it is 6. Now you substitute it back to the original algorithm and do the subtraction process. But now you can imagine that implementing the same algorithm again is very, very troublesome. So while long division is technically able to be generalized to cube roots, it will no longer be a practical method. For continued fraction, it will be even worse for cube roots. Remember how we painfully obtained the continued fraction expression for square root of 3. That is already quite good because it is periodic, and we can stop the process after a certain amount of steps. But continued fraction for cube roots is never periodic. We can actually prove this pretty easily. Let's say a number y can be written as a periodic continued fraction with period p. Let's say the repeating part is x. Then by writing x in full and replace the repeating part by x, we have this sort of monstrous equation. However, don't worry, because we can unveil the entire continued fraction on the right from the bottom. Eventually, we will end up with the equation x equals a plus bx divided by c plus dx, where a, b, c, and d are some constants. Rearranging, we have a quadratic equation in x. That means for a number to have periodic continued fraction expression, it has to be a root of a quadratic equation. This is definitely not the case for cube roots. With the non-periodicity and much higher difficulty to rationalize fractions with cube roots, using continued fractions to approximate cube roots is basically impractical. So is some generalization of the Babylonian method somewhat practical? Yes. We have in fact two different generalizations based on the two different explanations offered in the last video. Let's focus on the graphical or Newton's method first. In the previous video, we know that we can derive the iteration formula from the definition of derivative. In this case, the graph would be y equals x cubed minus a. So we can substitute the values of f of a0 and f prime of a0 respectively. With some manipulation, we get this formula. That means we can use this iteration to calculate cube roots. However, there is also a non-calculus method. we first start off with this inequality where we specify the distance between a0 and cube root of a to be smaller than some error bound epsilon, and cube the inequality. However, there is a new unwanted term, cube root of a squared. Don't worry, because we can first multiply both sides by cube root of a divided by a0. Now notice that these two boxed expressions can add up to cancel out each other, so we add them up to get this inequality. This is now close to what we want. Finally, multiply both sides by a0 divided by a plus 2a0 cubed, and we have this ultimate inequality. Now this boxed expression here would be a much better approximate than a0, so we write this as a1. So this means that from the non-calculus method, we have this iteration formula. These two separate methods yield the same iteration formula in square roots, but not in cube roots. So since they are different, can we tell which one is more efficient in calculating cube roots? To make the comparison fair, we use both methods to approximate the cube root of 2, using the initial guess 1. Now only with the first few iterations it is very clear that the non-calculus method is the winner, as it can produce 20 correct digits within only 3 iterations. So now, among the 3 different methods to calculate square roots, only Babylonian method can have a generalized version for cube roots that is practical for use. See if you can generalize Babylonian method to even higher order of roots. This is the end of a trilogy about surds. The next video is going to be a standalone one. Subscribe if you want more of these math videos. See you next time.